Okay, good morning, everyone. Chapter 1, Introduction to Electronics. So I'm going to talk a little bit about the difference between circuits and electronics and the classes that you take here at Cal Poly. So make sure I'm in the right section. 01. Okay. All right. So far, as an electrical engineering student, you have taken electric circuit analysis classes, right? You studied about resistors, capacitors, inductors, and circuit analysis techniques. And these are the exact same techniques that I learned when I was a student decades ago. Okay, everybody who is an E student learns about this worldwide. Fundamentals. The difference between electric and electronic is outlined here. Resistors, capacitors, and inductors are referred to as linear elements because the relationship of the voltage and the current is linear. So for a resistor, for example, you increase the voltage, current increases, and vice versa. You decrease the voltage, current decreases. Voltage and current have a linear relationship. Even for capacitors and inductors, we use differential equations, time dependent. Capacitor current is IC dV over dt. Inductor voltage is L di over dt, right? Derivative of time rate of change. But the relationship between the voltage and current for capacitors and inductors is also still linear. Hence, they are known as linear components. Electronic devices, on the other hand, made from semiconductors, do not have a linear relationship. So any semiconductor device, including diodes, transistors, FETs, MOSFETs, have a non-linear relationship. Hence, they are known as non-linear devices. So the voltage and current relationship for a diode, for example, you increase the voltage, the current is not going to increase in the same amount, the same proportion. And we will see that when we get to chapter 2, PN junctions. Okay, so that's the first big difference, linear versus nonlinear. Now, the analysis techniques that you learn are mostly analytical. Okay, analytical means they have exact solutions. You have Ohm's law, for instance, for a resistor, V equals IR. Barring any large variations in temperature or pressure or any other physical quantity like that, the Ohm's law equation is valid. Okay, especially when we talk about room temperature and normal conditions, Ohm's law is always valid. V equals IR, that describes the voltage and the current for a resistor. If you know 2 of the 3 quantities, you can calculate the third. So the analysis is analytical. It is always exact. For nonlinear devices, it is numerical. Numerical in this sense means it is approximate. We can never completely describe the behavior of a nonlinear device using solely one single equation. We have to build models. We have to build models that describes that nonlinear devices. And so we will study those models in 306. Excuse me. Allergies are acting up, so it's not something contagious. If you're sitting in the front row and getting worried. Okay, so
So numerical analysis is giving you an approximate solution. So you would use a model. You would use a model, analyze the circuit, see what the solution is. Does it fit your criteria? Does it describe your device? If it doesn't, go back to the top, try a different model, try a different equation, and perform the analysis again. So there's something known as iterative analysis. Okay, you do multiple iterations of the analysis until you arrive at a solution that completely describes your device operation. And analytical analysis is always exact. There is a parallel to be drawn between that question that I posted on the discussion, right? Describe yourself in 10 words or less. If you have only one word to describe yourself, it's possible to do so, but it does not describe you completely. You have 2 words, it describes you a little bit better. 10 words describes you even better. If you have an entire paragraph or an entire page, you could write an entire essay about yourself, right? In that same manner, if you have one equation with limited number of variables, it could describe the functioning of the device, but that model would not be valid in all conditions. You need an equation that has more variables that could completely describe the operation of this device. Okay. Hence, analytical versus numerical. Now, the classes you have taken at Cal Poly so far for electric circuits were 113, 211, and 212, right? But 113 is the foundation of everything. So you learn circuit analysis techniques in 113, and then you apply those techniques in 211 and 212. We'll also use those techniques going forward in 300 level classes, in 306 also. The same manner, 306 is the foundational course for electronic devices. You learn about semiconductors, semiconductor PN junctions, and then PNP junctions and NPN junctions, basically transistors. And you will learn how to develop models for these devices. You will develop models and learn analysis techniques. Then you go on to take 307 next quarter. 307 is digital circuits. You will take the models and the techniques you learned in 306 and apply it to create and develop digital logic circuits. It's the same transistors, but the transistor has several regions of operation, right? Several regions of operation. So depending on the region of operation, you can create either analog or digital circuits. And so 307 is all digital electronics. 308, you again use the fundamentals learned in 306 and apply it to develop analog circuits. Okay, so analog circuits 308. And then 409, which is electronic design, again, a required course for EE students. You take both analog and digital and combine them together to create mixed signal electronics. This is mixed signal electronics. Okay. Again, so that's why I say 306 is as important to your foundation as EE 113. A very common example of a mixed signal electronic device is your smartwatch or your smart devices. This is something I obtained from Sid Vyas, a colleague of ours here in the EE department. If you have a smart device, let's say a watch or a phone, it requires both sensors and computers, right? So digital electronic circuits will allow you to build switching circuits. Transistors are either on or off. Current and voltage is either available or not available. Okay, so binary, zeros and ones. The same device, when operated in the middle region between on and off, can be used as an amplifier, analog circuits. So a mixed signal device, like a smartwatch, has sensors, plus you need a computing and amplifying for those sensors. And so mixed signal electronic device. All right, let's take a 10-second pause. Let me know if you have any questions. Yes.
When you say like digital electronics, is that like creating those gates we use in like CPE when we talk about like logic gates and stuff like that?
That's one of the applications, yes. Logic gates. The question being asked is, would logic gates be an example of digital electronics? The answer is yes. Any other questions? Okay. All right, so the absolute first electronic device was the vacuum tube diode. So on the here, I have this evolution going in a clockwise manner. Actually, it's not clockwise. It goes from vacuum tubes to discrete transistors, and then to SSI and MSI circuits, and then VLSI circuits. But the absolute first device was a vacuum tube diode. So you had this kind of glass tube and the electrode inside it. That's referred to as a cathode. And you have another electrode at the far end referred to as the anode. Now, there used to be a filament in here to heat up the cathode. And it gets really hot. The cathode gets really hot. Electrons dissociate from the surface of the cathode. They float above the surface in close proximity. Right here. In the absence of any external energy source, the electrons will float above the surface. If you connect an external energy source, let's say a battery, between the two terminals, and the anode is now held at a positive voltage versus the cathode, the electrons are attracted to the positive charge and they start flowing towards the anode. Right here. And so that's the direction of the electron flow. And we say that the current is now flowing through the circuit because of the vacuum tube. And you're able to control the flow of this current, right? You're able to control the flow of this current by the external energy source that is applied. So this is the first and the earliest example of an electronic device, the vacuum tube diode. Diode, two electrodes. That's where the name comes from. Two electrodes. When they created solid state versions, meaning semiconductor version of the diode, the name carried over. They still refer to the solid state version as a diode, but that's the origin of that word. Even though we no longer have an electrode, in the truest sense, in a semiconductor diode. Now, as I was saying, you'd want to control the flow of current, but it's very hard to control the flow of current. So what they did was they inserted a third electrode in there to better able to control the flow of current. Okay. So now you have three electrodes, triode. And then instead of the fourth one, we went to diode, triode, quadrode, pentode, hexode, and so on and so forth. At one point, I remember I read about a researcher who inserted like 17 different electrodes inside a vacuum tube. So multiple electrodes in there, every single one, the function is, the point of doing that is to better able to control it so you can increase the functionality of that device. But after a certain point, I don't see the point. More trouble than it's worth. Vacuum tubes are kind of making a comeback in recent times.
So here, I believe this was a diode, and you can see these big ones right here. You can see the wraparound electrodes. The smallest one at the bottom left is probably about the size of our fingers, one single finger. And depending on, of course, the requirement, could be very thin, very small, or it could be large size. But that's the earliest example of a electronic device or electronic component. From there on, we went on to create discrete components. The discovery of the transistor, especially the silicon transistor. This, by the way, is still in use today, and you will be working with some of these in 346, the lab. Okay. From discrete transistors, we went to integrated circuits, meaning you take a large number of components, you integrate them onto one single piece of silicon die. So you're integrating large number of components on one single chip, hence the name integrated circuit, IC. The SSI and the MSI stands for small scale integration, medium scale integration, and then you have VLSI, very large scale. So you have SSI, MSI, LSI, and then VLSI. Okay, small scale integration, meaning smaller chip. You don't have that many components. Medium scale, you step it up a level. Large scale, much higher level, and then VLSI. Now we are probably in the VLSI, because we are now talking about billions of transistors on one small integrated circuit. There are probably not enough V's in the world to describe that integration. But everything is now just referred to as VLSI, very large scale integration. So, small, medium, large. It's like a McDonald's menu. Oh, referring to courses. So we are talking about integrated circuits, right? So what are integrated circuits? Integrated circuits are nothing but connection of components and wires. We have discrete components, right? You have component A, component B. It's a battery and a light bulb, and you have wires connecting the two. That's what a flashlight. You have a light bulb at one end, you have a battery, and there's a wire running across through the flashlight. Printed circuit board is simply a collection of components on a single board. I'm assuming everyone has seen one, right? You worked on one on 143, I believe. You created your own. All it is a bunch of wires connecting components. The wires are now just seem as if it's printed on top of that board, right? Hence the name printed circuit board, but it's just a bunch of wires. An integrated circuit is the exact same thing as a PCB, except it's at the micro scale. You have these tiny components on one single piece of board. In this case, it's silicon die. And then you have wires running from point A to point B, point C to point B. Okay. So it's just wires connecting different components. That's what a microchip is. If you want to learn how those are fabricated, we do offer a class. It's EE 423. It's actually offered in the BMed department, so it's cross-listed with EE. It is Intro to Micro Nano Fabrication, where you learn about the theory of semiconductor fabrication, semiconductor chip manufacturing. Okay, Ben Hawkins is EE/BMed professor. He teaches the lecture class. It's offered only one time a year in the winter quarter. And so if you wish to take it next year of next winter would be your chance to take that. And the associated lab class is EE 473, where students actually go into a clean room
and build micro devices. We take silicon wafers, about 25 of those, and we build diodes, transistors, solar cells, and resistors on that silicon wafer. Okay, so if that's something you're interested in, keep a lookout next winter. Not this coming winter, but next winter. So there's only one lecture class offered, one section of lecture class offered. The lab, associated lab has 3 sections, but it's again like 306 and 346. We have 36 students in the lecture class and 12 in the lab class. So you cannot take the lab class by itself. Let's see. Also, we have EE 422. Polymer electronics. This is also related to semiconductor chip manufacturing. Let's start right here in this building. Anyone guess which room? You might have passed by the room. And pay attention to the nameplate above the room. In room 105. So when you walk down the hallway, right after the CPE office, tech staff office is room 105. Started by a professor who's now retired, Dr. David Braun. It's a very ingenious way of actually creating a clean room inside the clean room environment in just a normal lab space. A clean room by its very name suggests that the environment is very clean. So let me go on a little bit of a tangent. I stated how PCBs and microchips are nothing but a bunch of wires connecting different components, right? On a PCB, you have a track going from, let's say, a resistor to a capacitor. If there's a break in the track, it's possible for you to like place a solder on it or maybe repair that connection, right? It's easy to do that. On a microchip, it's not possible. Microchip, you're laying down the road. If you're laying down a road and there's a rock or a boulder in the middle of your pathway, the road's not going to be built. Your wire will not work. So when you're talking about microchips, you're talking about dust particles that can be the size of huge boulders as far as the microchip is concerned. So the air needs to be completely devoid of very small dust particles that we can't even see. To give you an idea how small we're talking about, in a room like this, if you take a small cubic centimeter of space, there's about 1 million or 2 million particles, fine particles. In a clean room, comparable clean room will have less than 10. And higher level clean rooms will have less than 1. So that's class 1, class 10, class 100, class 1000. Clean room we have here on Cal Poly's campus. We do have a clean room, by the way, if you didn't know about it. There's an actual clean room facility here. That's where we teach that lab class. And that clean room, I believe, is class 1000. When I was a grad student at Louisville, we had class 1000 and 100. UCSB, the same thing, class 100 and class 1000. Academic clean rooms are usually about class 1000 and class 100. But that's something to keep in mind. If that piques your interest, you might want to keep a lookout for when that registration opens. Yes.
Polymer electronics like film capacitors or
No, we actually build organic light emitting diodes in that class. That's a good question. So the class is being asked, what is the class about? EE 422. So in the clean room environment, let me back up a bit. In a clean room environment, we go inside the room. The entire room is our working environment. We are gowned up from head to toe in white bunny suits to protect the environment. In room 105, Professor Braun and other tech staff decades ago, what they did was we stepped outside the environment. We created these, I want to say, chambers. If you've ever taken a look inside 105, you'll see there's a long chamber in there. So we are outside the environment and we interface with the internal environment by the use of long gloves. Okay. And so it's a very, I think it's a very clever solution to create a sort of a clean room, pseudo clean room environment in a, in a normal lab room. Those chambers are, by the way, that's not just his idea. Those chambers are, have been available for decades, okay, for decades. So he just took the idea and then implemented it to create this lab class. And so in polymer electronics, we use an organic polymer to create a light emitting diode, hence organic light emitting diode, OLED, which is the display technology that is in most electronic devices nowadays. So we're not creating anything that small, but the skills and the tools that we use are the exact same thing. All right, so you're to VLSI, surface mount. The modern electronics era really began in 1947. There were several discoveries made up to this point. So I like to call this is typically referred to as the first demonstration of a working transistor. I like to say it's one of the first because as with most discoveries, it's not just one person or doing the research. There were several researchers who had done work and published it in the years past, but this was the most important working demonstration of an actual semiconductor transistor. So the germanium point contact transistor, they were able to demonstrate the flow of current to that point contact transistor. The three people who were involved in this was at Bell Labs in 1947, John Bardeen, Walter Brattain, and William Shockley. All three of them really brilliant people. And well, as it so often happens with brilliant people, they always want to get stuff done. And so every once in a while, you'll come across brilliant people who are also kind of jerks, to say the least, to use a mild word. William Shockley was one of those kind of people. And you have your, famous billionaires, tech billionaires, they are very famous for being jerks. Well, the reason is those kind of people are always trying to push the envelope. So they always want, okay, I wanted this thing done yesterday. Why is it not done? That kind of thing. Anyway, everybody has personal opinions about those kind of people. But these three, Bardeen, Shockley, and Brattain, were awarded the Nobel Prize in Physics in 1953, I believe, 1953, for the demonstration of this transistor. So they are attributed as having discovered the transistor because it's the first working demonstration. Bardeen and Brattain left shortly thereafter. They were not involved anymore just because of differences with Shockley. Shockley then left Bell Labs after a while, and he started his own company with financing from some people. It came to be known as Shockley Semiconductor. And Shockley Semiconductor, his first 8 employees were these 8 PhD physicists who worked together on groundbreaking discoveries. But as it so happens, because of his nature, there were like lots of clashes. And then these 8 people, they left his employment. They actually tried to go over his head to the board or to the financiers, trying to get him removed or at least get him pushed aside. But then that didn't work. So then they left. And among those 8 people were 2 people known as Noyce and Moore, Robert Noyce and Gordon Moore. You are sitting in a classroom that is funded by Robert Noyce. This classroom falls under the Noyce School of Computing. The Noyce School of Computing was created due to a grant donated to Cal Poly by the widow of Robert Noyce. So Noyce and Moore left Shockley Semiconductor, went to Fairchild Semiconductor. From Fairchild Semiconductor, they left and went on to co-found. Anyone? Intel. Noyce, Moore, and Thiel. These are the 3 co-founders of Intel. Okay, the first 3 employees of Intel Corporation. So from transistors, we moved on to integrated circuits. Integrated circuits were invented, or let's say first working demonstration was in 1958. There was a near simultaneous development of integrated circuits. Okay, so you had discrete transistors, and then people and researchers were trying to get multiple components onto one single silicon die. Integrate, hence the name integrated circuits or ICs. Okay. Jack Kilby, and then Noyce and Moore at Fairchild. Jack Kilby at Texas Instruments are widely credited with the creation of the integrated circuit. Jack Kilby was awarded the Nobel Prize about 40 years later, somewhere in the late 90s. Okay. So he is credited with the invention of the integrated circuit. He is also credited as the inventor of the device that you use every single day as an engineering student, the calculator. Texas Instruments, that's where it comes from. Oh, another interesting fact about Bardeen is Bardeen went on to be a professor at Illinois, researcher at Illinois. He is one of only 5 people in the world to have won 2 Nobel Prizes, both in physics. He won first for the discovery of the transistor, and the second one for a theory postulating superconductivity. This was about 15, 20 years later. One of only 5 people. One of the other ones is Linus something, I can't remember. He was here, a West Coast guy from Oregon. He won the Nobel Prize in Physics and a Nobel Peace Prize, I believe. Marie Curie, she's the only woman to have 2 Nobel Prizes, and one of only 2 people, by the way, to have Nobel Prizes in 2 different fields. She won in physics and chemistry. Very interesting facts. And she, of course, won the Nobel Prize in Physics along with her husband, who was tragically killed in a road accident. But then she went on to head a research lab in Paris, in France. That research lab, then she employed her daughter and son-in-law, who also both went on to win Nobel Prizes. So, just some interesting factoids. All right. Now, Gordon Moore at Intel, when they first started working, they made rapid progress. Okay, made rapid progress in the technology, especially where discoveries of silicon. Silicon was very expensive to manufacture at a high level of purity early on. But once they found a reliable way to actually manufacture silicon, it became the de facto standard. Silicon is the second most abundant material on the planet. So there is, I wouldn't say unlimited, but a huge amount of supply. Okay. And so research has been done for several decades in silicon. And once they switched to making silicon transistors and silicon integrated circuits, rapid progress was made. And what Moore noticed was that the number of transistors they could fit onto one single piece of silicon, one small area, was doubling every 24 months. So at a conference, he was presenting a paper and he was talking about how the number of transistors is increasing. So he made a prediction. The prediction was that the number of transistors will double every 24 months for the foreseeable future. And he was probably talking about like maybe 10, 20, 30 years. Who knows? But somebody at the conference, maybe another engineer or maybe a colleague of his, took that prediction and coined the term Moore's Law. It's not really a law, obviously. It's a prediction, it's a theorem, if you will. But he postulated this theory, and then someone else coined the term Moore's Law, which states the number of transistors on a single die will double every 24 months. Okay. And then an engineer working at Intel said that it's even the pace of progress is even more rapid than what Moore is predicting. It's not 24. I see it doubling at 18 months. So every once in a while, you might see a conflicting account, whether Moore's law is 18 months or 24 months. But Moore was adamant that he never stated 18 months. He always stated 24 months. Okay, so if you talk about Moore's law, it's doubling every 24 months. And it seemed to hold true for most of the past several decades. We are now approaching the limits of what we can do with, current semiconductor fabrication techniques. We are now talking about at the atomic level, which, we are going into quantum computing and quantum mechanics. And so we are approaching the limit, and you can see it started to curve a little bit at the top. Right here. Because we're approaching the limits. Now, the reason we are able to squeeze more and more transistor devices on the same area is because the feature size keeps getting smaller. So on the left, you can see the feature size going from like 10 microns in the 1960s to less than 0.1 microns around the 2000s. The feature size refers to the size of the smallest feature on that device, on that microchip. Okay. If you have a small wire or a small piece of component, the entire component could be like 10 microns, but if the smallest feature in there was 1 micron, you would say the feature size of the entire device is 1 micron. In a way, it's kind of like a marketing gimmick. Not so much nowadays, but that's what it is. The smallest feature, the size of the smallest feature on the device is referred to as the feature size. So now we are talking about like nanometers and stuff, very, very small. Okay, as engineers, we deal with very large variation in numbers and values. We deal with very small numbers and very large numbers. So we use unit prefixes. Otherwise, you'd be like writing out like 9 and 10 zeros in every single value that you use. Okay, so here's a table with Greek letters. I expect each and every one of you to memorize the entire table. Be assessing this on the final exam. Okay. Not really. Even I don't remember this entire table. The final exam is open book anyway, so. But most of us are familiar with the middle of the table, right? We have milli, we have micro, nano. So let me give you an example of how small and how large these numbers mean. We can see and visualize 1 millimeter. We are familiar with 1 millimeter. If you take a meter, divide it into 1,000 parts, that's 1 millimeter. We use it in our rulers, our scales. We know it's very small. If you take 1 millimeter and divide it into further 1,000 parts, that is 1 micrometer, 10 raised to minus 6, or 1 micron. If you hear the words micron, that's what it means, 10 raised to minus 6 meters. A human hair, for instance, is about the size of 50 to 75 microns. Very, very thin. Okay, very, very thin. You ever use a mechanical pencil? It says 0.7 millimeters, 0.5 millimeters. 0.5 millimeters is 500 microns. You can still see it. So it's 500. If you divide it into 500 parts, that is 1 micron. Very small. And then if you take 1 micron and divide it into a further 1,000 parts, that is 1 nanometer. And we have already crossed that limit in terms of feature size. So we cannot even see 10 micron feature size without a microscope, let alone a nanometer. You need specialized equipment, specialized microscopes like SEMs and TEMs to view those devices. Okay, very, very small. But the reason we bring it up is because you're familiar with inductors, capacitors, currents, right? Inductors are typically in the millihenry range. Capacitors are typically in the microfarads or the nanofarads range. Currents are usually milliamperes, microamperes, even nanoamperes sometimes. Voltages are millivolts, right? So some of those are terms that you should definitely be familiar with without needing to look it up. And in the other side of the table, we have mega, giga, and tera, right? Everything's now like millions and billions and trillions. 10 raised to 3 is a kilo, 10 raised to 6 is mega, then giga, and then tera, 10 raised to 9, 10 raised to 12, so on and so forth. To give you an idea, of how large those numbers are, take a wild guess at how much is 1 million seconds in terms of hours, days, weeks.
30 years.
30 years? Not quite. It's a good guess. It's just about 11 days. How much do you think is 1 billion seconds? Now's your time to speak up. It is 31 years. You can speak up anytime, by the way. I was just saying the answer was correct. That's the difference between a billionaire and a millionaire. Stark difference. They like to throw out these numbers like, okay, the federal budget is now $3 trillion in deficit. And I was like, what do we talk? $3 trillion. It's like a huge amount of money. This is 1 billion seconds. 1 trillion, I don't even want to think about. That's 1,000 times 31. Right? 1,000 times 31. It's 3,000 years. They say that stadium costs like $2 billion to build. $2 billion is a lot of money. In terms of time, the difference is stark, right? Anyway, that's an example I like to use. Let's see. Okay, signal types and then notations. All right, so we will deal with analog signals and digital signals. The primary difference between analog and digital is that analog signals have infinite possibilities or infinite values at any given point in time, right? It is a continuous signal or continuous time signal, something that you studied in 228, right? When you take it with Clay?
Yes.
I heard that's an experience. So, but he's very good. Yeah, he's very good. It's not my wheelhouse. Maybe someday. So continuous time signals, analog, because the relationship, the signal has a value at any given point in time. There is no break. Okay. Digital signals, on the other hand, have discrete values. Okay, depending on the moment in time, the value will be separated by time. Okay. So continuous values and discrete values. And then we have often the need to convert between analog and digital. So we use ADC and DAC converters, or not converters, sorry. Analog to digital converters referred to as ADC, and DAC, which I believe you built in 143, DACs, digital to analog converters. Okay, so you have a need to go back and forth. Here you see a representation, a digital representation of this exact analog signal. What you're basically doing is you are actually sampling the signal at discrete points in time, at separated in time, right? So you sample the signal, so you take the value of the signal at one point in time, then in every regular intervals, you keep taking the values and you obtain an approximate representation of that analog signal. And you simply join the dots. That's how it would look. So it's not quite the exact same signal because it doesn't have same curves, right? What that means is the higher the number of samples, meaning the higher the sampling rate, the better is the description of your digital signal. And that is one of the big things. A real life example would be streaming video versus the physical disk. Right? A physical disk, the information is contained on the disk itself. Streaming video, you're constricted by the bandwidth of the internet, right? Bandwidth is basically the size of the road. Narrower the road, meaning basically the speed of the internet that you have, then the streaming quality will adjust, either go lower or higher depending on the internet speed that you have. Anyway, streaming video by its very nature is constricted by the internet speed. And so the number of bits per sample, number of bits per sample is far lower. So the bit rate is far lower You have higher resolution, but the number of bits basically describing that information is far lower. So streaming quality by its very nature would be slightly inferior to what you have on a disk. Anyway, that's a real life example. And then I have about 4 minutes left. Let's talk about notations. You are all familiar with this, but I do want to do a refresher. You have a single subscript notation and a two subscript notation that we use for our quantities, right? You have currents IAB, voltages VAB, simply means current going from A to B. In real life terms, it means you're measuring the current from A to with your reference set at B. If you're in the lab and you're asked to measure current IAB, then the positive end of the multimeter should go to A, negative end should go to B. The second subscript is always your point of reference. The common terminal of the meter should always go to the second subscript. IBA simply means you're measuring current going from B to A. And needless to say, IAB is minus IBA, and IBA is minus IAB. Okay. The plus and minus signs that we put are just for us humans. Current and voltage, like any other physical quantity, is never positive or negative, right? You would never say that your charger is minus 20 watts. Mathematically, we would say if you're supplying energy, it's minus. Otherwise, our equations would never balance out, right? So currents and voltages are never positive or negative inherently, but when we represent them mathematically, we put a notation on them, plus and minus. Same thing with voltages. Voltages need to have a reference point. So voltage VAB means you're measuring voltage at A with your reference at B. Plus, minus. And VBA, the exact opposite. You're measuring voltage at B with your reference at A. Then in the lab, when you're trying to measure these voltages, negative end should always go to the second subscript. Negative end of the meter or the common terminal of the meter should always go to the second subscript. And then the notations we use for our class, and these are pretty standard. Maybe you learned about this, maybe not, but we'll do a refresher anyway. We use uppercase. Sorry, uppercase. Lowercase quantities with uppercase subscripts. We'll be dealing with both AC and DC voltages and currents, meaning AC and DC signals in our electronic devices, right? So we need to refer, we use notations to refer to what is AC and what is DC. So a total signal comprising of both AC and DC voltages would have representation using lowercase alphabets, and the subscripts would be uppercase, mixed. If if it's all uppercase, it's DC. And if it's all lowercase, it's AC. The case in point, VT, total voltage, lowercase v, uppercase T, meaning you're talking about or you're referring to a total quantity comprising of AC and DC. DC is represented by all uppercase, AC is referred to by all lowercase. Okay. So we'll stop right here and I'll pick up here again on Friday. If you have any questions, I'm going to put this away and I'll have a few minutes before I go over to my office. Yes.
There's
That's scanned homework. So any any deadline or due date you see about scanned homework, it's not hard and fast deadline. Scanned homework is the work that you do for the online system and then you upload it. As long as it gets uploaded within a few days, that's fine. So if you see a deadline for a scanned homework, don't worry about it. Okay? I had to put in dates in there, otherwise Canvas does not allow us to, otherwise you would not be able to see those assignments. So I just, took homework 1, 2, 3, 4, 5, 6 and put in September 25th, 26th, 27th, 28th. So don't worry about those due dates. Yes.
I mean, since there's nothing assigned on the Connect yet, there's nothing.
No, Connect has been assigned. It's due tomorrow.
I didn't see it on there.
No, it's been assigned for a while. Several students have already done homework 0.
Oh,
Okay,
just
not,
tutorial.
Not one. Homework 0
Okay.
tutorials, yeah. Yeah. Oh,
Have you heard about the 1-inch square on Denmark at all?